Tonight, on the Science Pillow, we are stepping quietly into the vast, empty darkness between the Earth and the Moon. A distance so familiar it feels almost ordinary. 240,000 miles. A number repeated so often it has lost its weight. But tonight we are going to feel that distance again. We are going to understand what it truly means to leave this planet, to drift beyond the thin blue line of our atmosphere, and to fall silently toward a world that has not felt a human footprint in more than half a century. 54 years. That is how long it has been since a human being stood on the surface of the Moon and looked back at the Earth. 54 years since Eugene Cernan pressed his boot into the gray lunar dust for the final time, climbed the ladder of the Apollo 17 lunar module, and sealed the hatch behind him. He did not know it at the time, but he was closing a door that would remain shut for over 5 decades. The last human to walk on another world whispered his daughter's initials into the dust with his finger before he left. Those initials are still there, untouched, undisturbed, preserved in a vacuum where there is no wind, no rain, no erosion, and no sound. Just silence, stretching across the decades like a held breath. And now, finally, that breath is about to be released. 4 astronauts are preparing to leave the Earth and travel farther from home than any human being has ventured since December of 1972. Their names are Victor Glover, Reed Wiseman, Christina Koch, and Jeremy Hansen. They will not land on the Moon. Not this time. Their mission is something quieter, something more foundational. They will fly around it. They will loop behind the far side, where no communication with Earth is possible, where the silence is absolute and the darkness is total, and they will see something that only 24 human beings in the entire history of our species have ever witnessed with their own eyes. The Earth, reduced to a small, fragile, blue marble hanging in the blackness of space, slowly shrinking behind them as they drift deeper into the void. This is Artemis II, and tonight we are going to trace every step of this journey, from the moment the engines ignite on the launch pad to the moment the capsule splashes gently into the Pacific Ocean, 10 days later. We are going to understand the engineering, the physics, the human courage, and the quiet, ancient longing that has drawn our species toward the Moon since the first pair of human eyes looked upward and wondered what that pale light in the sky truly was. So, settle in. Let the weight of the day begin to fade. This is a calm, unhurried journey through one of the most extraordinary achievements in human exploration. Told gently, told slowly, and told with the kind of quiet wonder that the darkness of space deserves. There are no advertisements in this video, just the soft hum of the cosmos and the story of how we are finally going back. Part 1. The Last Footprint and the Long Silence. To understand why Artemis II matters, we must first understand what was lost. We must go back to December 14, 1972, to a narrow valley on the southeastern edge of the Moon called Taurus Littrow, where the final Apollo mission was drawing to a close. The valley itself is ancient beyond comprehension. It was formed roughly 3.8 billion years ago, during a period of cosmic violence known as the Late Heavy Bombardment, when the inner solar system was still being pummeled by the leftover debris of planetary formation. Massive asteroids, some the size of small countries, slammed into the lunar surface with enough force to excavate basins hundreds of kilometers wide. The impacts were so catastrophic that they cracked the Moon's crust down to its mantle, allowing molten basalt to seep upward and flood the newly formed craters, creating the dark, smooth plains we can see from Earth with the naked eye. The lunar Maria, the so-called seas of the moon, though they have never held a single drop of water. Taurus Littrow sits at the edge of one of these ancient flood basins, the Sea of Serenity. The valley is flanked by mountains that rise nearly 2,000 meters above the valley floor, taller than any peak in the Appalachian Range. These are not mountains formed by tectonic compression, as they are on Earth. They are the shattered, frozen remnants of an impact rim, heaved upward in a single cataclysmic instant billions of years ago, and then left utterly untouched by time. There is no weather on the moon, no wind, no rain, no rivers carving channels through the rock. The mountains of Taurus Littrow look today almost exactly as they did when they were formed, before the first single-celled organism appeared in Earth's oceans, before the continents coalesced, before anything alive had ever existed anywhere in the solar system, as far as we know. It was into this primordial landscape that astronauts Eugene Cernan and Harrison Schmitt descended in their lunar module, Challenger, on December 11, 1972. Schmitt was a geologist, the only professional scientist ever to walk on the moon, and he had spent years arguing with NASA administrators that the scientific value of sending a trained geologist to the lunar surface would far exceed the value of sending another test pilot. He was right. Within hours of arriving, Schmitt made one of the most significant discoveries of the entire Apollo program. While driving the lunar roving vehicle across the valley floor, Schmitt noticed something unusual in the regolith, the fine, powdery layer of crushed rock that covers the entire lunar surface. The soil was orange. Not the gray that every other Apollo crew had reported, but a distinct rusty orange that stood out sharply against the monochrome landscape. Schmitt immediately recognized its significance. The orange soil turned out to be composed of tiny glass beads, formed during ancient volcanic eruptions that had sprayed molten rock into the lunar vacuum. The beads were approximately 3.7 billion years old, tiny spheres of frozen fire from a time when the moon was still geologically active, when its interior was still hot enough to drive volcanic eruptions that would have been visible from the surface of the young Earth. This discovery fundamentally altered our understanding of the moon's thermal history. It proved that the moon had remained volcanically active for far longer than previous models had suggested, pushing back the timeline of lunar volcanism by hundreds of millions of years. Those tiny orange glass beads, smaller than grains of sand, each one a frozen droplet of ancient magma, told a story that reshaped planetary science. But the discovery also carried a deeper, more poignant significance that has only grown with time. Because after Schmitt collected his samples, after Cernan drove the rover for the last time and parked it a short distance from the lunar module so that the camera mounted on its front could film the departure, after the two men climbed back inside Challenger and sealed the hatch, no human being ever returned. Cernan's last words on the surface, spoken just before he ascended the ladder, were carefully chosen. He said, "As we leave the moon at Taurus Littrow, we leave as we came, and, God willing, as we shall return, with peace and hope for all mankind." He paused, then added, "America's challenge of today has forged man's destiny of tomorrow." Those words were meant to be a bridge, a promise that the departure was temporary, that humanity would return soon, perhaps within a decade, certainly within a generation. They were not meant to be an epitaph, but that is what they became. Eugene Cernan climbed into his spacecraft and left the moon, and behind him he left a silence that would last for 54 years, and counting. The footprints he left in the dust are still there. Every boot print, every rover track, every impression made by a human hand pressing against the surface to pick up a rock. All of it remains exactly as it was on that December day in 1972. On Earth, a footprint in the sand might last a few hours before the tide erases it. On the Moon, a footprint lasts for millions of years. There is nothing to disturb it. No atmosphere, no wind, no water. The only force that gradually softens the edges of a lunar footprint is the slow, patient rain of micrometeorites. Tiny particles of cosmic dust, smaller than a grain of sugar, drifting through space and occasionally striking the surface at tens of thousands of kilometers per hour. But even this process takes tens of millions of years to significantly alter a surface feature. The footprints of Apollo 17 will outlast every structure ever built by human civilization on Earth. They will outlast the pyramids. They will outlast the mountains. Long after the continents have shifted and the oceans have changed shape, those footprints will still be there, pressed into the ancient dust of Taurus Littrow, waiting. The question that has haunted space exploration ever since is simple, and it has no single answer. Why did we stop? The popular narrative is that we stopped going to the Moon because we lost interest, that the public grew bored, that the ratings for the Apollo missions declined after the first landing, that television networks stopped carrying the moonwalks live, and that the political will to fund such an expensive program simply evaporated once the primary objective, beating the Soviet Union, had been achieved. There is truth in this narrative, but it is incomplete. The real story is more complicated, more bureaucratic, and, in many ways, more instructive about how human civilizations make decisions about their own future. The Apollo program, at its peak, consumed approximately 4% of the entire United States federal budget. To put that in perspective, NASA's current budget hovers around 0.5%. 4% of the federal budget in the mid-1960s meant that roughly 4 cents out of every tax dollar collected by the government was being directed toward putting a human being on another world. This level of spending was not driven by scientific curiosity alone. It was driven by fear. In 1957, the Soviet Union launched Sputnik, the first artificial satellite to orbit the Earth. The event sent a shockwave through American society that is difficult to fully appreciate from the distance of decades. Sputnik was tiny, a polished metal sphere about the size of a beach ball, weighing less than 84 kilograms, carrying nothing but a simple radio transmitter that emitted a steady beep, beep, beep as it circled the globe every 96 minutes. But the implications of that beeping sphere were enormous. If the Soviet Union could place an object in orbit, it could, in principle, place a nuclear weapon anywhere on Earth with a flight time of minutes rather than hours. The space race was never primarily about exploration. It was about demonstrating the technological capability to deliver a warhead across an ocean in 30 minutes. President John F. Kennedy understood this calculus with perfect clarity. When he stood before a joint session of Congress on May 25, 1961, and declared that the United States would land a man on the Moon and return him safely before the end of the decade, he was not making a scientific proposal. He was making a strategic declaration. The Moon was a proxy. The real race was about intercontinental ballistic missile technology, about computing power, about materials science, about the capacity to manage enormously complex engineering projects under extreme time pressure. Everything that made a moon landing possible also made a more effective nuclear deterrent possible. And so the money flowed. At its peak, NASA employed over 400,000 people, either directly or through contractors. The Apollo program involved more than 20,000 industrial firms and universities. The Saturn V rocket, the vehicle that would carry astronauts to the moon, remains to this day the most powerful machine ever built by human beings. It stood 111 meters tall, taller than the Statue of Liberty, and produced 35 million newtons of thrust at liftoff, a force so staggering that the acoustic energy alone could kill a person standing too close. The sound of a Saturn V launch could be heard from over 160 kilometers away. But the moment Apollo 11 achieved its objective, the moment Neil Armstrong placed his boot on the lunar surface on July 20th, 1969, the strategic justification for the program began to dissolve. The race had been won. The Soviet Union's own lunar program, plagued by engineering failures, political infighting, and a series of catastrophic rocket explosions, quietly collapsed. Without a competitor, the urgency evaporated. Congress began cutting NASA's budget almost immediately after the first landing. Apollo 18, 19, and 20 were all canceled. The hardware had already been built. Flight-ready Saturn V rockets and lunar modules sat in warehouses and on display pedestals, museum pieces before they ever flew. The cancellation was not a dramatic moment. It was a slow administrative bleed. Budget hearings, committee reports, memos circulated between offices. The most ambitious engineering project in human history ended not with a grand proclamation, but with a series of accounting decisions made by people who would never be remembered by history. And then came the space shuttle. NASA, desperate to maintain relevance and funding in the post-Apollo era, proposed a reusable spacecraft that could launch like a rocket and land like an airplane. The shuttle was sold to Congress as an economical, routine transportation system that would make space access cheap and frequent. It was neither. The Space Shuttle program became one of the most expensive and complex operations in aerospace history. Each launch cost approximately $450 million in adjusted terms, and the turnaround time between flights was months, not the weeks that had been originally promised. More critically, the shuttle was designed exclusively for low Earth orbit. It could reach an altitude of roughly 600 kilometers at most. The moon is 1,000 times farther away. By committing to the shuttle program, NASA effectively locked itself into a vehicle that could not leave Earth's immediate neighborhood. For 30 years, from 1981 to 2011, American astronauts flew in circles around the Earth, never venturing more than a few hundred kilometers from the surface. They built the International Space Station, conducted thousands of experiments in microgravity, and performed hundreds of spacewalks. But they never left low Earth orbit. They never saw the Earth as a whole, sphere hanging in the darkness. They never experienced the silence and the scale that the Apollo astronauts had described. The astronauts who had walked on the moon grew older. Some became recluses, haunted by the strange psychological weight of having stood on another world and then being told, essentially, that it did not matter enough to go back. Buzz Aldrin struggled publicly with depression and alcoholism. Alan Bean left NASA and spent the rest of his life painting. Every single painting depicted the lunar surface. Michael Collins, who had orbited the moon alone in the command module, while Armstrong and Aldrin walked on the surface, wrote with quiet eloquence about the solitude of being, for a brief period, the most isolated human being who had ever lived, separated from every other person in existence by the entire width of the moon. One by one, they aged. One by one, they died. As of this recording, only 4 of the 12 men who walked on the moon are still alive. The youngest is 89 years old. The window of time in which humanity could speak to someone who had stood on another world and looked back at the earth was closing rapidly. And for decades, it seemed as though no one was coming to reopen it. Until Artemis. Part 2. The Architecture of Return. The Artemis program did not emerge from a single moment of inspiration. It grew, slowly and unevenly, from the wreckage of several previous attempts to return to the moon, each of which had been canceled, restructured, or defunded before reaching fruition. In 2004, President George W. Bush announced the Constellation program, which aimed to return Americans to the moon by 2020 using a new family of rockets and spacecraft. The program was canceled in 2010 by the Obama administration, which argued that the cost was unsustainable and the timeline unrealistic. However, Congress refused to let the program die entirely. The heavy-lift rocket that had been under development for Constellation, originally called Ares 5, was redesigned and renamed the Space Launch System, or SLS. The crew capsule, called Orion, survived the transition intact. These 2 components would become the backbone of what eventually evolved into the Artemis program. The name Artemis was chosen deliberately. In Greek mythology, Artemis was the twin sister of Apollo, the goddess of the moon, the hunt, and the wilderness. The naming was both a tribute to the original Apollo program and a statement of intent. Artemis would carry the first woman and the first person of color to the lunar surface. The program was formally announced in 2019, with an initial target of landing astronauts on the moon by 2024. A deadline that was quietly pushed back multiple times as engineering challenges, budget constraints, and the global disruptions of the early 2020s took their toll. But the hardware, slowly and painstakingly, came together. The Space Launch System is the most powerful rocket ever built. That statement requires careful qualification because the history of rocketry is full of superlatives that depend on how you measure power. The Saturn V produced more thrust at liftoff, but the SLS, in its Block 1 configuration, generates approximately 39 million newtons of thrust, more than enough to send the Orion spacecraft on a trajectory to the moon. The core stage is powered by 4 RS-25 engines, the same engines that powered the Space Shuttle. These are among the most tested and refined liquid fuel rocket engines in existence, each one representing decades of iterative engineering. They burn liquid hydrogen and liquid oxygen, producing an exhaust plume of superheated steam that exits the nozzle at approximately 4,400 meters per second. Flanking the core stage are 2 solid rocket boosters, each one standing nearly 55 meters tall and producing roughly 16 million newtons of thrust. These boosters burn a mixture of aluminum powder, ammonium perchlorate, and a synthetic rubber binder, a propellant that, once ignited, cannot be shut down. When those boosters light, there is no abort option that involves turning them off. They will burn for approximately 2 minutes, consuming their entire fuel, load, and then separate from the core stage at an altitude of roughly 45 kilometers. The combined thrust of the core stage engines and the solid rocket boosters, in the first seconds after ignition, produces a column of fire and steam so intense that the launch platform requires a sophisticated water deluge system that releases approximately 1.1 million liters of water in less than a minute to suppress the acoustic vibrations that would otherwise destroy the pad and potentially damage the vehicle itself. Above the core stage sits the Interim Cryogenic Propulsion Stage, or ICPS. This is a single-engine upper stage powered by a single RL-10 engine, one of the most reliable and longest-serving engines in American rocketry. The ICPS has one primary job. Once the core stage has exhausted its fuel and separated, the ICPS will ignite and perform the Translunar Injection Burn, or TLI. This is the moment that separates a trip to the Moon from a trip to low Earth orbit. Her TLI burn accelerates the Orion spacecraft from orbital velocity, approximately 28,000 kilometers per hour, to lunar transfer velocity, roughly 39,000 kilometers per hour. It is a controlled, precise increase in speed of approximately 11,000 kilometers per hour, executed over a burn duration of roughly 18 minutes. When the burn is complete and the ICPS separates, the Orion spacecraft will be on a trajectory that carries it beyond the gravitational dominance of the Earth and into the gravitational embrace of the Moon. And sitting at the very top of this entire assembly, above the ICPS, above the core stage, above the boosters, higher than the tip of a 30-story building, is the Orion spacecraft itself. This is where the crew lives. This is the capsule that will carry 4 human beings farther from home than any human has ever traveled. The Orion crew module is a deceptively simple shape. A truncated cone, roughly 5 meters in diameter at its widest point, with a habitable volume of approximately 9 cubic meters. That is roughly the interior volume of a large SUV. 4 adults will live inside this space for 10 days, while traveling 500,000 miles through the vacuum of space. The simplicity of the shape is deliberate. The conical form is the most aerodynamically stable configuration for atmospheric re-entry. When Orion returns to Earth at the end of the mission, it will be traveling at approximately 40,000 kilometers per hour, roughly 11 kilometers per second. At this velocity, the air in front of the heat shield cannot move out of the way fast enough, and is compressed into a superheated plasma that reaches temperatures of approximately 2,700 degrees Celsius. This is hotter than the surface of some stars. The heat shield on the base of Orion is the largest ablative heat shield ever built, measuring 5 meters in diameter and composed of a material called AV coat, a proprietary ablative compound that works by slowly burning away in a controlled manner, carrying the extreme heat away from the spacecraft as it vaporizes. The heat shield is designed to lose mass. Every gram of AV coat that burns away is a gram of thermal energy that does not reach the crew cabin. Behind the heat shield, the crew module is constructed from an aluminum-lithium alloy pressure vessel, surrounded by a composite outer shell. The walls are lined with a radiation-shielding material and thermal insulation. The interior contains 4 seats, though in the weightless environment of space, the distinction between sitting and floating becomes somewhat academic. The seats are arranged in 2 rows, with the commander and pilot in the front row and the 2 mission specialists behind them. Each seat is equipped with a customized cushion molded to the specific body shape of the astronaut who will occupy it, designed to distribute the forces of launch and re-entry evenly across the body to minimize the risk of injury. The life support system is a marvel of closed-loop engineering. The atmosphere inside Orion is maintained at roughly sea-level pressure, 101 kilopascals, with a composition of approximately 21% oxygen and 79% nitrogen, identical to the air you are breathing right now as you listen to this. Carbon dioxide, exhaled by the crew, is scrubbed from the air by a system of lithium hydroxide canisters that chemically absorb CO2 molecules. Water vapor is collected, filtered, and recycled. The cabin temperature is maintained between 18 and 27 degrees Celsius by a system of heat exchangers and coolant loops that transport waste heat to radiator panels on the exterior of the spacecraft, where it is radiated into the cold of space as infrared light. One of the most remarkable engineering features of the Orion spacecraft is its thermal management of the deep space environment. In low Earth orbit, the thermal environment is complex but predictable. One side of the spacecraft faces the Sun and can reach temperatures of over 120 degrees Celsius, while the shadowed side drops to minus 150 degrees Celsius. But in deep space, beyond the protective influence of Earth's magnetic field and far from the thermal buffering effect of the planet's reflected heat, the thermal extremes become even more challenging. Orion uses a system called the Active Thermal Control System, which slowly rotates the spacecraft along its longitudinal axis, a maneuver called a barbecue roll, to distribute solar heating evenly across all surfaces. This gentle, continuous rotation, taking approximately 1 revolution per hour, prevents any single side of the spacecraft from overheating or freezing. The astronauts inside barely notice the rotation. Their world turns slowly, silently, as the stars drift past the small windows in an endless, patient procession. The service module, attached to the base of the crew module, is called the European Service Module, or ESM. It was designed and built by the European Space Agency, making Artemis an international endeavor from its structural foundations. The ESM provides propulsion, electrical power, and thermal control for the duration of the mission. It is powered by 4 solar array wings that span a total of 19 meters when fully deployed, converting sunlight into approximately 11 kilowatts of electrical power. The main engine of the ESM is a single orbital maneuvering system engine, originally designed for the Space Shuttle. This engine provides the thrust necessary for course corrections, orbital adjustments around the Moon, and the critical trans-Earth injection burn that will send the crew home. The ESM also carries the spacecraft's consumables, the water, oxygen, and nitrogen that the crew will need for the duration of the mission. It is, in every functional sense, the life raft. Without the service module, the crew module is a sealed tin can with no propulsion, no power, and a limited supply of breathable air. This dependency is why the service module is jettisoned only at the very last moment before re-entry. Just minutes before the crew module hits the atmosphere, the explosive bolts fire, the umbilical connections sever, and the service module tumbles away into the Pacific sky, burning up as it falls. The crew will not see this happen. By then, they will be pressed into their seats by the decelerating forces of atmospheric friction, watching the windows glow orange with plasma, listening to the roar of air against the heat shield after 10 days of almost perfect silence. The transition from the void of deep space to the violence of re-entry takes approximately 20 minutes, and then the parachutes deploy. 2 drogue chutes first, to slow and stabilize the capsule, followed by 3 massive main parachutes, each one over 30 meters in diameter, blooming like enormous orange and white flowers against the blue sky. The capsule descends gently, swaying beneath its canopy of silk and nylon, and touches down in the Pacific Ocean at a speed of roughly 32 kilometers per hour. Gentle enough to be survivable, rough enough to be memorable. But all of that, the re-entry, the parachutes, the splashdown, is the ending. To understand the mission itself, we need to follow the trajectory from the beginning. We need to understand the path these 4 astronauts will take through the emptiness between the Earth and the Moon, and what they will see and experience along the way. Before we trace the trajectory, it is worth pausing to consider the 4 human beings who will be strapped into those custom-molded seats when the solid rocket boosters ignite and the launch platform disappears beneath them in a column of fire and steam. Commander Reed Wiseman is a former Navy test pilot and a veteran of one previous spaceflight. He spent 165 days aboard the International Space Station in 2014, during Expedition 40 and 41. During that mission, he conducted 2 spacewalks totaling 13 hours outside the station, working in the hard vacuum of low Earth orbit, while the Earth rotated slowly beneath him. Wiseman is responsible for the overall conduct of the mission. In the event of an emergency, his decisions are final. Pilot Victor Glover is also a former Navy test pilot. He served as pilot on the SpaceX Crew Dragon Resilience mission in 2020, spending 167 days aboard the International Space Station. Glover will be the first person of African descent to travel beyond low Earth orbit. This fact carries a weight that extends far beyond the technical parameters of the mission. For the entirety of the Apollo program, from 1968 to 1972, every astronaut who left low Earth orbit was a white American male. The astronaut corps of that era was drawn almost exclusively from the military test pilot community, which was itself a product of the deeply segregated institutions of mid-20th century America. Glover's presence on Artemis II does not erase that history, but it does represent a meaningful expansion of who gets to see the Earth from the distance of the Moon. Mission specialist Christina Koch is a physicist and electrical engineer. She holds the record for the longest single spaceflight by a woman. 328 consecutive days aboard the International Space Station, from March 2019 to February 2020. During that mission, she participated in the first all-female spacewalk alongside astronaut Jessica Meir. Koch's background is in the physics of space environments. Before joining NASA, she worked at the Johns Hopkins University Applied Physics Laboratory and spent time at research stations in the Arctic and Antarctic, environments that in some ways mirror the isolation and confinement of long-duration spaceflight. Mission specialist Jeremy Hansen is a fighter pilot with the Royal Canadian Air Force and a member of the Canadian Space Agency. He has never been to space before. Artemis II will be his first spaceflight, and it will take him not merely to low Earth orbit, but directly to the Moon, a trajectory that will carry him nearly 400,000 kilometers from Earth on his very first mission. Hansen will be the first Canadian and the first non-American to travel beyond low Earth orbit. His selection reflects the increasingly international character of lunar exploration. Artemis is not an exclusively American program, but a coalition involving the space agencies of Europe, Japan, Canada, and several other nations. These 4 individuals have spent years training for this mission. They have practiced emergency procedures in underwater simulations, in centrifuges that replicate the forces of launch and re-entry, in full-scale mock-ups of the Orion cabin where every switch, every display, every piece of equipment is replicated with exacting fidelity. They have studied the trajectory. They have memorized the abort modes. They have rehearsed the scenarios in which things go wrong. Engine failures, communication blackouts, pressure leaks, radiation events, until the correct responses are embedded so deeply in their muscle memory that they could execute them while exhausted, disoriented, or injured. But no amount of simulation can fully prepare a human being for the moment when the engines ignite and the vehicle begins to rise. The Saturn V astronauts described the launch as being inside a building that was falling apart. Vibrations so intense that they could not read the instruments on the panel in front of them. Noise so overwhelming that it penetrated the helmet, the suit, and the bones of the skull. The SLS launch will be comparable. For approximately 2 minutes, while the solid rocket boosters are burning, the crew will experience forces of roughly 4 GHE, 4 times the pull of Earth's gravity, pressing them into their seats. Their arms will feel as though they are made of lead. Their vision may narrow slightly as the blood in their bodies is forced downward. And then, quite suddenly, the boosters will separate. The ride will smooth out dramatically, and the core stage engines will continue to accelerate them toward orbit at a more manageable rate. 8 minutes and 36 seconds after liftoff, the core stage engines will shut down. The main engine cutoff, MECO, is followed by stage separation and a sudden absolute silence. The vibrations stop. The roar stops. The crew is weightless. Objects that were pressed firmly into surfaces begin to float. Dust motes drift in the cabin air like tiny planets in a miniature solar system. The transition from the violence of launch to the serenity of weightlessness is one of the most dramatic sensory shifts a human being can experience. And then they wait. For approximately 2 hours, the Orion spacecraft and its attached ICPS will orbit the Earth, systems being checked, trajectories being confirmed, ground controllers verifying that every parameter is within acceptable limits. During this time, the crew can look out the windows and see the Earth passing beneath them at a speed of roughly 28,000 kilometers per hour. They will cross the entire continental United States in about 9 minutes. They will see the thin blue line of the atmosphere, a band of air so narrow relative to the size of the planet that it would be invisible if it were not illuminated by the sun. This thin, fragile layer is all that separates the living world from the killing vacuum of space. Everything that has ever lived, everything that has ever breathed, everything that has ever thought a thought or felt an emotion, all of it exists within that paper-thin shell of gas clinging to the surface of a rock hurtling through the void at 107,000 kilometers per hour. And then, when all systems are confirmed and the trajectory is verified, the ground controller will give the command, and the ICPS engine will ignite for the translunar injection burn. Part 3. The Journey. The translunar injection burn is the moment everything changes. Before TLI, the spacecraft is in Earth orbit. It is close to home. It could, with a relatively simple deorbit burn, return to the surface within an hour. After TLI, the spacecraft is on a trajectory that will carry it to the Moon. The commitment is made. The distance begins to grow. The single RL-10 engine of the ICPS ignites in the silence of orbit. There is no roar in space. The crew feels a gentle push, roughly 1/10 of a G, barely enough to notice, and the velocity of the spacecraft begins to climb. Over the course of approximately 18 minutes, the engine adds roughly 11,000 kilometers per hour to the spacecraft's velocity. When the burn is complete, Orion is traveling at approximately 39,000 kilometers per hour relative to the Earth. This is fast enough to escape the gravitational grip of low Earth orbit and begin the long, curving fall toward the Moon. Shortly after the I-burn is complete, the ICPS separates from the Orion spacecraft. The spent upper stage drifts away, tumbling slowly, catching the sunlight on its metallic skin as it recedes. It will eventually enter a heliocentric orbit, an orbit around the Sun rather than the Earth, becoming another piece of human-made debris in the vast, mostly empty space between the planets. The Orion spacecraft, now on its own, deploys its solar arrays and begins the coast phase of the mission. The coast to the Moon takes approximately 4 days. 4 days of silence. 4 days during which the Earth shrinks from a massive, overwhelming presence filling the windows to a progressively smaller disk of blue and white. This shrinking is one of the most psychologically significant experiences reported by Apollo astronauts. There is a phenomenon known as the overview effect, a cognitive shift reported by nearly every astronaut who has seen the Earth from a sufficient distance. It is described as a sudden visceral understanding that the Earth is a single, interconnected system, that the political borders and national identities that define human society are invisible from space, and that the planet is startlingly small, startlingly fragile, and startlingly alone in the darkness. The Apollo 8 astronaut William Anders, who was among the first humans to see the Earth from lunar distance in December 1968, described the experience in terms that were almost religious. He said that they had gone to the Moon to explore it, but what they had really discovered was the Earth. The famous photograph he took, Earthrise, showing the blue and white Earth rising above the gray lunar horizon, became one of the most influential images in human history. It is credited with catalyzing the modern environmental movement because for the first time, human beings could see their planet as a whole, and seeing it whole meant seeing it as vulnerable. The Artemis II crew will experience this same cognitive shift, but with a crucial difference. The Apollo astronauts saw the Earth shrinking through small porthole-style windows. The Orion spacecraft has larger windows, and the crew will have modern digital cameras capable of capturing images at resolutions the Apollo astronauts could never have imagined. They will photograph the Earth from the distance of the Moon with equipment that can resolve individual weather systems, volcanic plumes, and the light of cities on the night side. These images, when transmitted back to Earth, will become the defining visual documents of a new era of exploration. During the 4-day coast, the crew settles into a routine. They monitor systems. They perform scheduled experiments. They eat meals from pouches, thermostabilized foods, and freeze-dried meals that are rehydrated with hot or cold water from the spacecraft's supply. They sleep in sleeping bags tethered to the walls of the cabin, because in weightlessness there is no up or down, no bed to lie on, no mattress to press against. Sleep in space is a peculiar experience. Without the familiar sensation of weight pressing the body against a surface, the brain struggles to fully relax. Many astronauts report that it takes several nights to adjust. Some describe the sensation of floating in their sleeping bags as peaceful, womb-like. Others find it disorienting and difficult. The spacecraft rotates slowly, the barbecue roll, and through the windows, The stars process in a stately, silent parade. The sun passes by, impossibly bright, followed by the deep, velvet blackness of space in the opposite direction, where the stars are so numerous and so vivid, without an atmosphere to scatter their light, that the entire sky seems filled with a fine, glittering dust. The Milky Way is not a faint smudge in the sky, as it appears from the surface of the earth in all but the darkest locations. From space, it is a vast, luminous river of light that stretches from horizon to horizon, thick with stars, clouds of gas and dark lanes of cosmic dust that have been drifting through the galaxy for billions of years. And ahead, growing slowly larger with each passing hour, is the moon. From the Earth's surface, the moon appears as a flat, luminous disk, a circle of silver or gold pressed against the dome of the sky. It seems two-dimensional, like a painting, like a decoration hung on a ceiling of black velvet. But as the Orion spacecraft draws closer, the moon begins to reveal its true nature. It transforms from a disk into a sphere. It acquires depth, texture, dimension. The dark areas, the Maria, become distinct from the bright, heavily cratered highlands. The terminator, the line between the illuminated and shadowed hemispheres, becomes a razor-sharp boundary where sunlight meets absolute darkness. The approach to the moon is not a straight line. The spacecraft follows a curved trajectory dictated by the interplay of gravitational forces from the Earth, the moon, and the sun. As Orion draws closer to the moon, the lunar gravity begins to dominate, pulling the spacecraft faster and curving its path. The crew can watch the moon grow in the windows over the course of hours, its surface becoming increasingly detailed. Individual craters become visible. The great ray systems, bright streaks of ejected material radiating outward from young impact craters like Tycho and Copernicus, stand out with startling clarity against the darker basalt of the Mare Plains. The surface of the moon, seen up close, is a record of violence. Every feature, every crater, every mountain range, every valley was created by an impact. The moon has no atmosphere to burn up incoming objects, no tectonic activity to recycle its surface, no weather to erode its features. Everything that has ever struck the moon has left a permanent scar. The surface is saturated with craters. Craters within craters, ancient impacts, overlapping with more recent ones, the entire history of the inner solar system's bombardment written in stone and dust. The largest visible feature on the near side is the Oceanus Procellarum, the ocean of storms, a vast, dark plain of solidified basalt that stretches over 2,500 kilometers across the northwestern quadrant of the near side. Despite its name, it has never known a storm, never known weather of any kind. The name was given by 17th century astronomers who believed the dark areas might be actual seas. By the time humanity developed telescopes powerful enough to resolve the surface in detail, the names had already stuck. The Sea of Tranquility, the Sea of Serenity, the Sea of Crises, the Ocean of Storms. Beautiful, poetic names for a world that is utterly, profoundly lifeless. As the spacecraft approaches the moon, the crew prepares for the powered flyby, the critical maneuver that will carry them around the far side. The approach trajectory is designed so that the spacecraft passes behind the moon at an altitude of approximately 128 kilometers above the surface. This is close enough that the crew will be able to see individual boulders on the crater floors, close enough to distinguish the subtle color variations in the regolith. the faint blues and oranges that indicate differences in mineral composition. And then something extraordinary happens. The spacecraft passes behind the moon, and the Earth disappears. This is not a gradual process. The Earth does not slowly set below the lunar horizon like a sunset. It simply vanishes. One moment it is there, a bright blue crescent hanging in the sky, the only source of color in the universe, and the next moment the bulk of the moon has moved between the spacecraft and the Earth, and there is nothing but blackness and stars. The far side of the moon is not dark. It receives exactly as much sunlight as the near side. The term dark side is a misnomer that has persisted in popular culture despite being scientifically inaccurate. The far side is simply the hemisphere that permanently faces away from the Earth due to tidal locking. The moon rotates on its axis at exactly the same rate it orbits the Earth, so the same face is always turned toward us. But the far side has a dramatically different appearance from the near side. It has almost no Maria, almost no dark basaltic plains. Instead, it is almost entirely covered in bright, ancient, heavily cratered highland terrain. The crust on the far side is thicker than on the near side, which prevented the volcanic floods that created the Maria from reaching the surface. The result is a landscape that looks more ancient, more battered, and more alien than anything visible from Earth. The crew will see this landscape passing beneath them at a speed of roughly 6,000 kilometers per hour. They will photograph it with equipment that can capture details as small as a few meters across. And during this transit of the far side, a period lasting approximately 30 minutes, they will be completely cut off from communication with Earth. No radio signals can pass through the solid rock of the moon. Mission Control will hear nothing. The crew will transmit nothing. For half an hour, 4 human beings will be more alone than any human beings have ever been, separated from their entire species by 250,000 miles of vacuum and the full width of another world. The Apollo astronauts who experienced this loss of signal described it in remarkably similar terms. Michael Collins, orbiting alone in the Apollo 11 command module, while Armstrong and Aldrin walked on the surface below, wrote that during each pass behind the far side, he felt simultaneously the most isolated and the most serene he had ever felt in his life. The silence was not frightening. It was absolute. It was, he said, the silence of a cathedral, not empty, but full of a vast, patient presence. The Artemis II crew will experience this same silence, this same isolation, knowing that on the other side of the moon, 384,000 kilometers away, 8 billion people are going about their lives, completely unable to reach them, completely unable to hear them, completely unable to help them if anything goes wrong. And then, as the spacecraft continues along its trajectory, the Earth will reappear. It will rise above the limb of the moon. Earthrise. And the crew will see their planet emerge from behind the gray lunar horizon like a jewel ascending from behind a veil of stone. This moment, the return of the Earth to the view of human eyes after its brief disappearance, is described by every Apollo astronaut who experienced it as the single most emotionally overwhelming moment of the mission. Not the launch, not the landing, the moment when the Earth came back. The trajectory of Artemis II is not arbitrary. It has been designed with a specific safety philosophy in mind, a concept called a free return trajectory. This is one of the most elegant solutions in orbital mechanics, and understanding it reveals the careful, almost anxious caution with which NASA has approached this mission. A free return trajectory is a flight path that uses the Moon's gravity, rather than the spacecraft's engines, to curve the vehicle's course and send it back toward the Earth. The beauty of this approach is that if the spacecraft's main engine fails completely, if it cannot perform any propulsive maneuver at all, the natural gravitational dynamics of the Earth-Moon system will still return the spacecraft to the vicinity of the Earth, allowing for a re-entry and splashdown. The crew does not need to fire an engine to come home. Gravity does the work. This is not a theoretical contingency. It has been used in a real emergency. Apollo 13, launched in April of 1970, suffered a catastrophic failure when an oxygen tank in the service module exploded approximately 320,000 kilometers from Earth. The explosion destroyed the service module's fuel cells, eliminating the primary source of electrical power and oxygen for the command module. The crew, James Lovell, Jack Swigert, and Fred Hayes, was forced to shut down the command module entirely and retreat into the lunar module, which served as a lifeboat for the return journey. The spacecraft was on a free return trajectory, and although a small engine burn was required to adjust the flight path and shorten the return time, the fundamental principle held. The Moon's gravity curved the trajectory and flung the spacecraft back toward Earth without requiring the main engine of the crippled service module. Artemis II will follow a similar, though not identical, free return path. The spacecraft will approach the Moon, pass behind the far side at a closest approach of approximately 128 kilometers, and then use the Moon's gravity to curve its trajectory and send it on a wide, sweeping arc that carries it approximately 70,000 kilometers beyond the Moon, farther from Earth than any human being has ever traveled, before beginning the long fall back toward home. The total distance from Earth at the farthest point of the trajectory, the apogee of the lunar flyby, will be approximately 450,000 kilometers. To put this in perspective, the International Space Station orbits at roughly 400 kilometers above the Earth. Artemis II will carry its crew more than 1,000 times farther from the surface than any astronaut aboard the space station has ever been. The light from Earth, traveling at 300,000 kilometers per second, will take approximately 1.5 seconds to reach the spacecraft at its most distant point. When Christina Koch speaks into the radio at maximum distance, her words will take 1.5 seconds to reach mission control, and the reply will take another 1.5 seconds to return. A 3-second round-trip delay. It sounds trivial, but it represents a fundamental change in the nature of communication. For the first time, the crew will experience a perceptible lag in conversation with Earth. They will speak, and then they will wait, floating in silence, for the reply to arrive from a planet that is no longer close enough for instantaneous conversation. The return journey takes approximately 4 days. The spacecraft falls back toward the Earth, accelerating under the planet's gravitational pull, growing faster and faster as it approaches. By the time it reaches the outer edges of the atmosphere, it will be traveling at approximately 40,000 kilometers per hour, fast enough to cross the entire Atlantic Ocean in about 7 minutes. The re-entry angle must be controlled with extreme precision. If the spacecraft enters the atmosphere too steeply, the deceleration forces will exceed the structural limits of the vehicle and the physiological limits of the crew. If it enters too shallowly, it will skip off the atmosphere like a stone skipping across water and fly back out into space, potentially on a trajectory from which recovery is impossible. The acceptable re-entry corridor is approximately 40 kilometers wide. 40 kilometers at a distance of 400,000 kilometers, after a 10-day journey through deep space. The margin for error is roughly 1/100th of a degree. This is the precision required to bring 4 human beings home safely from the Moon. Part 4. The Moon. While the Artemis II crew will not set foot on the lunar surface, their mission is a necessary precursor to the missions that will. And to understand why returning to the Moon is scientifically important, not merely symbolically important, it is worth considering what the Apollo missions left behind, both physically and intellectually. The physical artifacts of Apollo are scattered across 6 landing sites on the near side of the Moon. At each site, the descent stage of the lunar module remains where it landed, its legs still resting on the regolith, its gold foil thermal insulation still glinting faintly in the sunlight. Around each descent stage, the tracks of the astronauts are preserved in the dust. Boot prints, tool marks, and, at the later landing sites, the twin tracks of the lunar roving vehicle winding across the surface like the trails of some mechanical animal. The Apollo astronauts also left behind a collection of scientific instruments that, remarkably, continued to function for years after the crews departed. The Apollo Lunar Surface Experiments packages, ALSEP, included seismometers that detected moonquakes for nearly a decade after they were deployed. These instruments revealed that the Moon is not geologically dead, as had been previously assumed. The Moon experiences regular seismic events, some caused by tidal stresses from the Earth's gravity, some by the thermal expansion and contraction of the surface as it cycles between the brutal heat of the 2-week lunar day and the extreme cold of the 2-week lunar night, and some by impacts. Perhaps the most enduring scientific instrument left on the Moon is the Lunar Laser Ranging Retroreflector, a simple array of precisely manufactured corner cube reflectors designed to bounce laser beams directly back to their source. Observatories on Earth fire powerful laser pulses at these reflectors and measure the time it takes for the light to return, allowing scientists to calculate the distance between the Earth and the Moon with an accuracy of approximately 1 millimeter. Over the decades since Apollo, these measurements have revealed extraordinary facts about the Earth-Moon system. The Moon is slowly receding from the Earth at a rate of approximately 3.8 centimeters per year, roughly the same rate at which human fingernails grow. This recession is caused by tidal interactions between the two bodies, the same interactions that cause the ocean tides on Earth. As the Moon pulls on the Earth's oceans, creating tidal bulges, the rotation of the Earth carries those bulges slightly ahead of the Moon's position, and the gravitational pull of the forward bulge exerts a gentle, persistent tug on the Moon, accelerating it slightly and pushing it into a progressively higher orbit. 3.8 centimeters per year does not sound like much, but over the 4.5 billion-year history of the Earth-Moon system, it accumulates dramatically. When the Moon first formed, likely from the debris of a cataclysmic collision between the young Earth and a Mars-sized body called Theia, it was roughly 15 times closer to the Earth than it is today. It would have appeared enormous in the sky, a looming, terrifying presence filling a significant portion of the visual field. The tides it generated were immensely more powerful, creating ocean bulges hundreds of meters tall that swept across the surface of the early Earth in relentless, world-shaping cycles. Over billions of years, the Moon slowly spiraled outward, and the tides gradually weakened, and the Earth's rotation gradually slowed. Because the same tidal interaction that pushes the Moon away also acts as a brake on the Earth's spin. The days are getting longer. 4 billion years ago, an Earth day was roughly 6 hours long. In another few billion years, the Earth and Moon will reach a state called tidal lock, where the Earth's rotation will have slowed to match the Moon's orbital period, and the two bodies will forever face each other with the same hemisphere, frozen in a gravitational embrace that will persist until the Sun itself dies. These are the kinds of truths that the Moon has to teach us, deep, patient, ancient truths about the nature of gravity, time, and the slow, inexorable mechanics of celestial bodies. And Artemis is designed to uncover more of them. The future landing sites for the Artemis program are concentrated around the lunar South Pole, a region that was never visited by the Apollo missions, and that has become, in the years since, one of the most scientifically tantalizing locations in the solar system. The south pole of the Moon is unlike any other place on the lunar surface. Because the Moon's axis of rotation is tilted only 1.5 degrees relative to the plane of its orbit around the Sun, compared to the Earth's 23.5-degree tilt, the poles experience almost no seasonal variation. The Sun never rises more than a few degrees above the horizon at the poles. This means that the bottoms of deep craters near the poles are permanently shadowed. Sunlight has not touched the floors of these craters for billions of years. They are among the coldest places in the entire solar system, colder than the surface of Pluto, with temperatures that can drop below minus 230 degrees Celsius. And in that permanent darkness, protected from the sun's heat and the erosive effects of solar wind, there is water. The presence of water ice in the permanently shadowed craters of the lunar South Pole was first confirmed definitively by NASA's Lunar Crater Observation and Sensing Satellite, LCROSS, in 2009. The mission involved deliberately crashing a spent rocket stage into a permanently shadowed crater called Cabeus, near the South Pole, and then flying a trailing spacecraft through the resulting plume of ejected material to analyze its composition. The plume contained water. Not a trace amount, but a significant concentration, an estimated 5.6% water ice by mass in the regolith of the crater floor. Subsequent measurements by India's Chandrayaan missions and NASA's Lunar Reconnaissance Orbiter have confirmed that water ice exists in dozens of permanently shadowed craters across the South Polar region. The total amount of water trapped in these cold reservoirs is difficult to estimate precisely, but some models suggest it could be in the range of hundreds of millions of metric tons. This water is ancient. It was likely delivered to the Moon over billions of years by comet impacts and asteroid collisions, and possibly also by the interaction of solar wind protons with oxygen-bearing minerals in the regolith, a process called solar wind implantation. Once deposited in the permanently shadowed craters, the water molecules migrated along the surface through a process of ballistic hopping, bouncing from point to point in the near-vacuum environment until they fell into a cold trap deep enough and dark enough that they could never escape. There they accumulated, layer by layer, molecule by molecule, over billions of years, building up deposits of ice mixed with regolith in the eternal darkness of the crater floors. The scientific significance of this water is profound. It represents a pristine record of the volatile delivery history of the inner solar system. By analyzing the isotopic composition of the ice, the ratio of deuterium to hydrogen, for example, scientists can determine whether the water came from comets, asteroids, or solar wind, and potentially trace the origin of Earth's own oceans. There is a possibility, still debated but increasingly supported by evidence, that a significant fraction of the water in Earth's oceans was delivered by the same population of comets and asteroids that deposited water on the Moon. If the lunar ice has the same isotopic signature as Earth's ocean water, it would be powerful evidence that our oceans are, in a very real sense, extraterrestrial in origin. But the water also has practical significance that extends far beyond pure science. Water can be split into hydrogen and oxygen through electrolysis. Oxygen is breathable. Hydrogen and oxygen, recombined, are rocket propellant, the same propellant that powers the main engines of the SLS and the Space Shuttle. If future Artemis missions can extract water from the permanently shadowed craters and process it into propellant, the Moon becomes not just a destination but a fuel depot, a way station for deeper exploration of the solar system. A spacecraft launched from the lunar surface, where the gravity is only 1/6 of Earth's, requires dramatically less energy to escape into interplanetary space. A moon with accessible water and the infrastructure to convert it into fuel becomes the logical departure point for missions to Mars and beyond. The engineering challenge of extracting water from permanently shadowed craters is formidable. These are not gentle environments. The temperature at the bottom of a permanently shadowed crater hovers around 30 to 40 degrees above absolute zero. At these temperatures, most metals become brittle. Lubricants freeze solid. Battery chemistry ceases to function. Any robotic system sent into these craters must be designed to operate in conditions that are, in many ways, more extreme than those found anywhere else in the solar system, including the surface of Mars. The regolith in these craters is expected to be a mixture of dry, powdery soil and ice. Not a solid block of frozen water, but a complex matrix of tiny ice crystals intermixed with mineral grains. Extracting the water would likely involve heating the regolith to sublimate the ice, converting it directly from solid to gas, bypassing the liquid phase entirely in the near vacuum of the lunar surface, and then capturing and condensing the water vapor. The energy required for this process is substantial, and it would need to come from solar power arrays positioned on the crater rims, where they could receive sunlight, with the power transmitted down into the shadowed interior via cables or microwave beams. There are also peaks near the lunar south pole that are in almost permanent sunlight, the so-called peaks of eternal light. These elevated points, sitting on the rims of polar craters, receive sunlight for more than 90% of the year, making them ideal locations for solar power generation. The proximity of permanent shadow and permanent sunlight at the lunar south pole creates a unique energy landscape, a place where, within a few kilometers, you can find both the coldest and the most consistently illuminated locations on the entire Moon. This juxtaposition is one of the primary reasons the South Pole has been selected as the focus of the Artemis landing program. The implications extend beyond the Moon itself. If humanity can demonstrate the ability to extract and process resources on the lunar surface, what aerospace engineers call in situ resource utilization, or ISRU, it establishes a precedent and a technology base that can be applied to Mars, to the asteroids, and to any other body in the solar system where resources exist. The Moon becomes a proving ground not just for exploration, but for the development of an entirely new capability. The ability to live and work in space using the materials that space provides, rather than carrying everything from Earth. This is the strategic vision that underpins the Artemis program. Artemis II, The mission carrying Glover, Wiseman, Koch, and Hansen around the moon and back is the first crude step in a plan that ultimately aims to establish a permanent human presence on the lunar surface, to build the infrastructure for lunar resource utilization, and to use the moon as a stepping stone to the deeper solar system. But that is a story for the future. For now, in the quiet darkness of this night, 4 astronauts are preparing to do something simpler and, in its own way, more profound. They are preparing to leave the Earth and see the moon up close, to experience the silence and the scale and the overwhelming beauty of the cislunar void, and to bring that experience back to the rest of us. Returning from the moon is, in many ways, more dangerous than getting there. The outbound journey is a controlled, gradual acceleration followed by a long, peaceful coast. The return is a violent, compressed deceleration that compresses the kinetic energy of a 10-day journey into approximately 20 minutes of controlled fire. When Orion re-enters the Earth's atmosphere, it will be traveling at approximately 11 kilometers per second. At this velocity, the spacecraft possesses an enormous amount of kinetic energy that must be converted into heat and dissipated before the vehicle can slow down enough for the parachutes to deploy safely. The physics of this conversion is governed by the principles of gas dynamics and thermodynamics that have been understood since the earliest days of rocketry. But the engineering challenge of surviving the process remains among the most demanding in aerospace. As the spacecraft descends into the upper atmosphere, it encounters air molecules at increasingly higher densities. At 11 kilometers per second, the air cannot move out of the way of the approaching vehicle fast enough. Instead, it is compressed into a thin layer of superheated plasma in front of the heat shield, a shock wave that reaches temperatures of approximately 2,700 degrees Celsius. This is roughly half the temperature of the surface of the sun. The heat shield glows. The air around it glows. From a distance, the spacecraft would appear as a bright orange-white streak across the sky, a miniature meteor carrying 4 human beings. The AV coat material of the heat shield is designed to manage this thermal assault through a process called ablation. As the outer surface of the heat shield reaches extreme temperatures, the AV coat material undergoes a controlled chemical decomposition. It pyrolyzes, breaking down into gases and char. These gases are injected into the boundary layer between the heat shield and the shock wave, creating a thin, insulating buffer that pushes the hottest plasma slightly away from the solid surface. The heat shield literally sacrifices itself, layer by layer, to protect the spacecraft behind it. By the time the vehicle has slowed to subsonic speeds, several centimeters of heat shield material will have been consumed, vaporized into the atmosphere, carrying the thermal energy of re-entry away with it in a cloud of gas and glowing particles. Inside the cabin, the crew experiences the deceleration as a sustained, heavy pressure pushing them into their seats. The peak deceleration can reach approximately 6 Joule, 6 times the force of gravity. A person who weighs 80 kilograms on the ground would feel as though they weigh 480 kilograms during the peak deceleration. Breathing becomes difficult. Vision narrows. Every movement requires enormous effort. The experience lasts for several minutes, and then, gradually, the forces ease as the spacecraft slows. The plasma dissipates. The glow fades. The sky outside the windows transitions from a blinding, fiery orange to a calming, familiar blue. And then the parachutes deploy. The drogue chutes come first, 2 small parachutes that deploy at an altitude of roughly 7.5 kilometers at a speed of roughly 500 kilometers per hour. Their purpose is not to slow the capsule significantly, but to stabilize it and orient it correctly for the main parachute deployment. Once the capsule is stable and below a certain speed, the main parachutes deploy. 3 enormous canopies, each one over 30 meters in diameter, that billow open in a precisely sequenced cascade. The capsule jerks upward, or rather, its descent rate drops dramatically, and then it hangs beneath its 3 parachutes, swaying gently, descending at approximately 32 kilometers per hour toward the surface of the Pacific Ocean. The splashdown is not gentle, but it is survivable. The capsule hits the water with a force comparable to a minor car accident. It bobs upright, supported by inflatable airbags that deploy on impact to keep it oriented correctly in the water. Recovery helicopters and naval vessels are already in position nearby, having tracked the capsule's descent by radar and by visual observation. Within minutes, divers are in the water, attaching a flotation collar to the capsule and securing it for recovery. The hatch opens. The salt air of the Pacific Ocean floods into a cabin that, for the past 10 days, has contained nothing but recycled, filtered, temperature-controlled air. The crew breathes in the smell of the sea, salt, moisture, the faintly organic scent of the open ocean. And for a moment, after 10 days of processed air and vacuum and the absolute sterility of space, the simple act of breathing natural air from the surface of their own planet is overwhelming. They are home. They have been to the moon and back. And the door that was closed in December of 1972 is at last open again. Part 5. Why we go back, there is a question that has been asked, with increasing frequency, by people who look at the cost of the Artemis program, estimated at over $90 billion through the first several crewed landing missions, and wonder whether the money could be better spent on terrestrial problems. It is a fair question, and it deserves a thoughtful answer. The simplest response is that the investment in space exploration has historically generated returns that far exceed its cost, through technological innovation, through scientific knowledge, and through the expansion of human capability. The Apollo program, despite its enormous expense, produced technologies that permeated every aspect of modern life. Water purification systems developed for the Apollo spacecraft are now used in developing countries to provide clean drinking water. The miniaturization of computing hardware required to fit navigation computers into the Apollo command module accelerated the development of integrated circuits that led, within a few decades, to the personal computer and the smartphone. Materials science advances from the heat shield program found applications in fireproof clothing, insulation, and medical devices. The economic return on the Apollo investment, by most estimates, exceeded the original cost by a factor of 7 to 14. But the deeper answer is not about economics. It is about the nature of our species. Human beings are, fundamentally, an exploring species. We walked out of Africa roughly 70,000 years ago, not because the savanna was uninhabitable, but because something in the architecture of the human mind compels us to look at a horizon and wonder what lies beyond it. We crossed oceans in wooden boats. We climbed mountains that served no practical purpose. We mapped the deep ocean floor. We sent robots to Mars. We pointed telescopes at the edge of the observable universe and peered 14 billion years into the past. The moon is the next horizon. Not because it is easy, and not because it is economically justified in the narrow terms of quarterly earnings and annual budgets, but because it is there, and because we are the kind of species that goes to places that are there. Artemis is not the final destination. It is the first step on a path that leads to Mars, to the asteroid belt, to the outer planets, and eventually, perhaps, to the stars themselves. The distances involved in those future journeys are so vast that they defy human intuition. Mars, at its closest approach, is roughly 55 million kilometers from Earth, more than 140 times the distance to the Moon. A crewed mission to Mars, using current propulsion technology, would take approximately 7 months each way, with the crew spending over a year on the Martian surface waiting for the orbital mechanics to align for the return journey. The total mission duration would be approximately 2.5 years. The astronauts would be farther from home than any human being has ever been, for longer than any human being has ever been away, in an environment more hostile than any place on Earth. The Moon is where we learn how to do this. It is where we learn how to live off the land in space, extracting water, manufacturing propellant, growing food in sealed habitats, maintaining equipment in a vacuum, and coping with the psychological challenges of extreme isolation. It is where we make our mistakes, close enough to home that a rescue mission is feasible, rather than making those mistakes on Mars, where a rescue mission is physically impossible with current technology. This is why Artemis II matters. Not because it will land on the Moon, it will not. Not because it will make a scientific discovery that changes our understanding of the universe, though it may contribute to future missions that do. Artemis II matters because it reopens the door. It proves that the hardware works, that the trajectory is sound, that the heat shield can protect the crew during a deep space re-entry, and that 4 human beings can travel to the Moon and return safely. It is the engineering validation that makes everything that follows possible. And for the crew, for Glover, Wiseman, Koch, and Hansen, it is something more personal and more profound. It is the experience of leaving the Earth and seeing it whole, of understanding in a way that no photograph or description can fully convey how small and fragile and beautiful the planet is, of floating in the void between 2 worlds and feeling the silence of the cosmos press against the thin walls of their spacecraft, like the weight of deep water. Every phase of the Artemis II mission has been designed with a corresponding set of emergency procedures, contingency plans that the crew has rehearsed hundreds of times in simulators, plans that they hope never to use but are prepared to execute without hesitation. These are the abort modes, and understanding them reveals a side of spaceflight that is rarely discussed in the language of wonder and exploration. It is the language of engineering caution, of worst-case scenarios, of quiet, systematic preparation for disaster. The most dangerous phase of the mission is the first 2 minutes, the period during which the solid rocket boosters are burning. During this time, if a catastrophic failure is detected, a structural breakup, an uncontrollable deviation in the flight path, a loss of cabin pressure, the crew's only option is the Launch Abort System, or LAS. This is a tower-shaped structure mounted on top of the Orion capsule, equipped with a set of solid-fuel abort motors capable of generating approximately 1.8 million newtons of thrust in a fraction of a second. If the abort is triggered, the LAS motors ignite, pulling the Orion capsule away from the failing rocket with a force of approximately 15 G, 15 times the force of gravity. The crew would experience this as an instantaneous, crushing acceleration that would press them so deeply into their seats that breathing becomes nearly impossible. The entire abort sequence, from motor ignition to capsule separation, takes approximately 15 seconds. 15 seconds to separate a crewed spacecraft from a failing rocket that is producing 39 million newtons of thrust and carrying hundreds of thousands of kilograms of explosive propellant. The launch abort system has never been used in an actual emergency on a crewed mission. It was tested successfully in an uncrewed flight test, Ascent Abort 2, in July of 2019, during which the abort motors were fired at maximum dynamic pressure conditions, and the capsule was successfully separated from a simulated booster and recovered by parachute. The test validated the system, but there is an enormous psychological difference between validating a system with an empty capsule and knowing that 4 human beings are relying on it to save their lives. After the solid rocket boosters separate, approximately 2 minutes into the flight, the abort options become somewhat more flexible. The core stage engines, the 4 RS-25s, can be shut down on command, unlike the solid boosters. If a problem develops during the core stage burn, the crew has several options depending on the altitude and velocity at the time of the failure. If they have gained enough altitude and speed, they can separate from the core stage and use the ICPS to achieve a stable orbit, from which they can perform a deorbit burn and return to Earth. If they have not gained sufficient altitude, they can perform what is called an intact abort, using the Orion's service module engine to guide the capsule to a landing zone in the Atlantic Ocean, downrange from the launch site. Once the spacecraft is in orbit and preparing for the trans-lunar injection burn, a new category of risk emerges. The ICPS, the upper stage, that performs the TLI burn, is powered by a single RL-10 engine. If the engine fails to ignite for TLI, the mission is over, but the crew is safe. They are in a stable orbit around the Earth and can perform a deorbit burn using the service module engine to return home. The mission would be classified as a failure to achieve primary objectives, but no lives would be lost. The most concerning failure scenario occurs after TLI, when the spacecraft is en route to the Moon and beyond the reach of a quick return. If the service module's main engine fails during the cislunar transit, if it cannot perform the course corrections or the trans-Earth injection burn needed to return home, the free return trajectory becomes the crew's lifeline. As we discussed, the free return path uses the Moon's gravity to curve the trajectory back toward Earth without requiring any engine burns. But the free return trajectory, while it guarantees a return to the vicinity of Earth, does not guarantee a precisely targeted re-entry. Without the ability to make fine adjustments, the re-entry angle might be slightly off nominal. The crew would survive, but the landing zone might be hundreds of kilometers from the planned recovery area, requiring a longer search and rescue operation in potentially challenging sea conditions. There are deeper failure scenarios that the public rarely hears about. A micrometeorite strike that penetrates the pressure hull, causing a slow depressurization. A failure of the thermal control system, leading to a gradual, inexorable rise or fall in cabin temperature. A malfunction in the carbon dioxide scrubbing system, leading to a slow buildup of CO2 that causes headaches, confusion, and eventually unconsciousness. For each of these scenarios, the crew has trained responses: emergency patches for pressure leaks, backup cooling systems, spare lithium hydroxide canisters. But every contingency has limits. Every backup system has a finite capacity. And at the distances involved in a lunar mission, help is not coming. There is no rescue spacecraft standing by on a launch pad. There is no quick return. The crew must solve every problem with the resources they have on board, or they do not solve it at all. This is the reality of deep space exploration that exists beneath the poetry of Earthrise and the beauty of starlit windows. It is a reality of risk management, of probabilistic analysis, of engineering margins that are calculated to be sufficient but can never be guaranteed. The astronauts know this. They have read the reports. They have studied the failures of Apollo 13, of Columbia, of Challenger. They have sat in briefing rooms and listened to engineers describe, in calm, technical language, exactly how things can go wrong, and exactly how quickly a survivable situation can become an unsurvivable one. And they have decided to go anyway. Not because they are reckless, but because they understand that exploration has always involved risk, that no meaningful extension of human capability has ever been achieved without the possibility of failure, and that the alternative, staying safely on the ground, never venturing beyond the familiar, is a kind of failure in itself, a failure of nerve, a failure of imagination, a failure to honor the restless, reaching impulse that has defined our species since the first human being looked at a mountain and decided to climb it. Not because there was food at the top, but simply because it was there. Artemis II is a flyby mission. It does not include a lunar landing, but it is designed to validate the systems and the trajectory that will be used for Artemis III and the missions that follow. Missions that will land astronauts on the lunar surface for the first time since 1972. And those future missions will rely on an element of infrastructure that does not yet exist, but is being designed and built right now, a small space station in lunar orbit called the Gateway. The Gateway is, in concept, an outpost, a way station, a place where crews can stop, transfer vehicles, stage equipment, and conduct research without having to descend to the lunar surface or return to Earth. It will orbit the Moon in what is called a near rectilinear halo orbit, or NRHO, a highly elliptical orbit that brings it as close as 3,000 kilometers to the lunar surface at its nearest point and carries it out to approximately 70,000 kilometers at its farthest. This orbit was chosen for a combination of practical reasons. It requires very little fuel to maintain. It provides good communication coverage with both the lunar surface and the Earth, and it offers regular opportunities for spacecraft to arrive and depart. The Gateway will be small by space station standards. The International Space Station, which has been continuously occupied since November of 2000, has a pressurized volume roughly equivalent to a 6-bedroom house. The Gateway's initial configuration will have a pressurized volume closer to that of a studio apartment. It will consist of 2 primary modules, the power and propulsion element, built by Maxar Technologies, which provides electrical power from large solar arrays, and ion propulsion for orbital maintenance, and the Habitation and Logistics Outpost, or HALO, built by Northrop Grumman, which provides the living and working space for the crew. The station will not be permanently occupied. Unlike the ISS, which has hosted a continuous human presence for more than 25 years, the Gateway will be visited by crews for periods of weeks or months, and then left unoccupied between visits. During the uncrewed periods, it will operate autonomously, maintaining its orbit, collecting scientific data from instruments mounted on its exterior, and waiting for the next crew to arrive. The scientific potential of the Gateway extends beyond its role as a logistics hub. Instruments mounted on the station could study the lunar surface from orbit with a level of detail and duration that is impossible for a spacecraft simply flying past. They could monitor the radiation environment of cislunar space, providing data critical for understanding the long-term health effects of deep space radiation on human beings. They could serve as a relay station for robotic rovers operating on the far side of the Moon, which is permanently out of direct radio contact with Earth. By placing the gateway in an orbit that has line of sight to both the lunar far side and the Earth, it becomes possible, for the first time, to communicate with and control robots on the hemisphere of the Moon that no human has ever seen from the surface. The gateway also introduces a new paradigm in how humans travel to and from the lunar surface. In the Apollo program, the entire vehicle stack, the command module, the service module, and the lunar module traveled together from Earth to the Moon and back. This meant that the lunar module had to be carried all the way to the Moon, even though it was only used for the final descent and ascent. This is enormously wasteful in terms of mass and fuel. The Artemis architecture separates these functions. The Orion spacecraft carries the crew from Earth to the gateway. At the gateway, the crew transfers to a dedicated lunar lander, in the case of Artemis II, a variant of SpaceX's Starship, which descends to the surface and then returns to the gateway. The crew then transfers back to Orion for the journey home. This modular approach is more complex operationally, but it is far more efficient in terms of mass. It also opens the possibility of reusing the lunar lander for multiple missions, rather than discarding it after each landing as Apollo did. A reusable lander, fueled by propellant manufactured from lunar water ice, could dramatically reduce the cost of each subsequent surface mission. The first few landings will be expensive, resource-intensive affairs. But the 10th landing, the 20th, the 50th, each one could cost a fraction of the first as the infrastructure matures and the supply chains become established. This is the vision. It is ambitious, it is expensive, and it is, by any historical measure, achievable. Human beings have built space stations before. They have landed on the Moon before. They have manufactured fuel from local resources on Mars. The Perseverance rover's MOXIE experiment successfully demonstrated the production of oxygen from the Martian atmosphere. Each individual component of the Artemis architecture has precedent. What is new is the combination, the integration, the scale. And it all begins with Artemis II, with 4 astronauts in a capsule, flying around the Moon and back, proving that the systems work, that the heat shield holds, that the trajectory is sound, and that human beings can once again leave the shallow orbit of the Earth and venture into the deep, quiet, ancient darkness of cislunar space. The gateway will wait. The surface missions will follow. The South Pole ice will be sampled and analyzed and, eventually, processed into the water and propellant that will sustain a permanent human presence on another world. But tonight, in this moment, it is enough to know that the first step is being taken. That the silence of 54 years is ending. That the footprints in the dust of Taurus Littrow will, at last, have company. Part 6. The Silence Between Worlds. There is a kind of silence that exists only in space. It is not the silence of an empty room, or the silence of a quiet forest, or the silence that falls over a city at 3 o'clock in the morning. Those are all silences defined by the absence of something, the absence of conversation, or traffic, or birdsong. They are silences that exist within a medium that could carry sound, but happens not to be carrying any at the moment. The silence of space is fundamentally different. It is not the absence of sound within a medium. It is the absence of the medium itself. There is no air. There is no substance to vibrate. Sound, which is nothing more than a pressure wave propagating through a material, simply cannot exist. If you were standing on the surface of the moon without a helmet, which you would not survive for more than a few seconds, and someone fired a cannon next to you, you would see the flash but hear absolutely nothing. The gunpowder would burn. The projectile would fly. The gases would expand. But without air to carry the pressure wave to your ears, the entire event would be as silent as a dream. The Artemis II crew, during their transit behind the far side of the moon, will experience a version of this silence that is augmented by an additional layer of isolation. For approximately 30 minutes, as the moon's bulk blocks the line of sight between the spacecraft and the Earth, all radio communication will cease. This is not a technical failure. It is physics. Electromagnetic waves, including radio signals, travel in straight lines. They can't bend around a solid object the size of the moon. During the far side transit, the crew's communication system will produce nothing but static, or more precisely, the faint, random hiss of cosmic background radiation, the afterglow of the Big Bang, a whisper of microwave energy that has been traveling through space for 13.8 billion years. This background radiation, the cosmic microwave background, fills every cubic centimeter of the universe with a faint, uniform glow of microwave energy that corresponds to a temperature of approximately 2.7 degrees above absolute zero. It is the oldest light in existence. The light from the moment, roughly 380,000 years after the Big Bang, when the universe cooled enough for hydrogen atoms to form and for light to travel freely through space for the first time. Before that moment, the universe was an opaque fog of plasma, free electrons and protons scattering photons in every direction, making the cosmos as impenetrable to light as the interior of a star. Then the temperature dropped below 3,000 degrees. The electrons were captured by protons to form neutral hydrogen, and suddenly, for the first time in the history of existence, light could travel in a straight line without immediately colliding with a charged particle. That light has been traveling ever since. It has been stretched by the expansion of the universe from visible light, the kind of light your eyes can see, into microwaves, electromagnetic radiation with wavelengths measured in millimeters rather than nanometers. It fills all of space. It is everywhere. It is the faint, residual warmth of the universe's birth, stretched thin across billions of years of cosmic expansion, still measurable, still present, still whispering its ancient story to anyone with a sensitive enough antenna to listen. The Artemis II crew, during their 30 minutes of radio silence behind the moon, will be surrounded by this whisper. It is the only signal that reaches every point in the universe, the only communication that has never been interrupted since the cosmos became transparent, the only message that the universe has ever broadcast continuously, in every direction, for every moment of its existence. And its content, when decoded by cosmologists, tells the story of everything: the density of matter, the rate of expansion, the geometry of spacetime, the age of the universe, and the seeds of every galaxy, every star, every planet, and every living thing that would eventually emerge from the primordial plasma. The crew, floating in their capsule behind the moon, surrounded by this ancient universal whisper, cut off from every other human voice, will be closer to the fundamental nature of the cosmos than almost any human being has ever been. They will not hear the cosmic microwave background, of course. It is far too faint and the wrong frequency for human ears. But they will be bathed in it, immersed in it, as intimately close to the birth cry of the universe as it is physically possible for a human being to be. And outside their windows, the stars will burn. Thousands of them, millions of them, each one a nuclear furnace converting hydrogen into helium at temperatures of millions of degrees, each one radiating light into the void in all directions, each one so distant that its light takes years or centuries or millennia to reach the human eye. The nearest star to our Sun, Proxima Centauri, is approximately 4.2 light-years away. The light leaving Proxima Centauri right now will not reach Earth until the year 2030. The light from the most distant galaxies visible to the James Webb Space Telescope has been traveling for over 13 billion years, since a time when the universe was less than 5% of its current age. The crew of Artemis II, looking out at this ocean of ancient light, will see the universe not as it is, but as it was, a mosaic of different moments in cosmic history, assembled by the finite speed of light into a single, breathtaking panorama. The stars they see are not where they appear to be. They are where they were, years or centuries ago, when the light that is now entering the astronaut's eyes began its journey. Some of the stars they see may no longer exist. They may have already collapsed or exploded or faded into darkness, and the news of their death is still traveling across the void, a message that has not yet arrived. This is the universe that Artemis II will carry its crew through. A universe of ancient light and absolute silence, of distances that make human timescales seem comically brief, of forces and energies that dwarf anything in human experience. And, in the middle of it all, 4 human beings in a small metal capsule, breathing recycled air, eating rehydrated food, sleeping in tethered bags, looking out at the cosmos through windows no larger than a dinner plate, and feeling, if the reports of every astronaut who has ever left low Earth orbit are to be believed, a profound, humbling, transformative sense of peace. On February 14, 1990, the Voyager 1 spacecraft, which had been launched 13 years earlier and was now 6 billion kilometers from Earth, passed the orbit of Neptune, heading toward the boundary of the solar system, turned its camera back toward the inner planets, and took a final photograph of Earth. The image, captured from such an immense distance, showed the Earth as a tiny, pale blue point of light, barely distinguishable from the background noise of the camera sensor, suspended in a sunbeam that happened to streak across the frame. The astronomer Carl Sagan, who had championed the idea of taking the photograph, wrote about it with a clarity and emotional depth that has rarely been matched. He observed that every human being who had ever lived, every king and peasant, every young couple in love, every inventor and explorer, every teacher and every child, every creator and destroyer of civilization, had lived their entire lives on that tiny point of light. That all of human history, every war, every famine, every triumph, every act of kindness and every act of cruelty had taken place on a mote of dust suspended in a sunbeam. The Artemis II crew will not see the Earth from the distance of Voyager 1. They will see it from a distance of roughly 450,000 kilometers, close enough to resolve the continents, the oceans, the swirl of weather systems, and the faint glow of city lights on the night side. But the emotional impact, based on the testimony of every astronaut who has experienced it, is remarkably similar. The Earth, seen from the distance of the Moon, does not look powerful. It does not look dominant. It does not look like the center of anything. It looks small. It looks fragile. It looks like something that could easily be broken, and like something that desperately needs to be protected. This is the gift that Artemis II will bring back to Earth. Not rocks, not soil samples, not scientific data, though data will certainly be collected. The gift is perspective. The gift is the understanding, earned through the direct experience of leaving the planet and seeing it whole, that the Earth is a single, interconnected, staggeringly beautiful system, and that every human being who has ever lived is a passenger on this small, blue, improbable world, drifting through the darkness of space at 100,000 kilometers per hour, warmed by a single, ordinary star, protected by a thin shell of gas and a fragile magnetic field, and sharing a destiny that is, whether we acknowledge it or not, entirely collective. And so tonight, as you lie here in the quiet darkness, consider this. Every atom in your body was forged in the heart of a star that burned and died billions of years before the Earth was born. The calcium in your bones, the iron in your blood, the oxygen you are breathing at this very moment, all of it was manufactured in the nuclear furnaces of ancient suns, scattered into space by supernova explosions, gathered by gravity into the cloud of gas and dust that eventually collapsed to form the solar system, and assembled, over 4.5 billion years of patient chemistry, into the living, breathing, thinking being that you are. You are not merely a creature of the earth. You are a creature of the universe, made of the same material as the stars, the same material as the moon, the same material as the spacecraft that will soon carry 4 human beings on a journey to our nearest celestial neighbor and back. You are stardust, arranged in a pattern complex enough to wonder about its own origin, and tonight you are lying in the dark, listening to the story of how your species is learning to leave the world that made you and venture out into the cosmos that you came from. Every breath you take contains atoms that have been recycled through the bodies of billions of organisms over the 4.5 billion year history of life on Earth. The oxygen molecule entering your lungs right now may have once been part of a fern in a carboniferous swamp, or a plankton in a Jurassic ocean, or a molecule of water that fell as rain on a mountain that no longer exists. Ter is not created or destroyed. It simply changes form. It flows through the world like water through a landscape, gathering in pools of complexity, a cell, a body, a mind, and then dispersing again into the great, slow, turning cycles of the Earth and the cosmos. You are one such pool of complexity, temporary and extraordinary, resting now in the quiet darkness while the Earth carries you through space at a speed you cannot feel. Let this gentle exploration of the journey from the Earth to the Moon settle softly into your thoughts. Breathe slowly. Feel the weight of the day dissolve into the vastness of the space that surrounds this small, warm, turning planet. Imagine the silence of the cislunar void, the slow rotation of the spacecraft, the patient drift of starlight through windows no larger than the palm of your hand. The moon is waiting. It has been waiting for 54 years, and soon, very soon, human beings will see it up close again, and they will look back at the Earth, and they will see what only a handful of people in all of history have ever seen. The whole of the human world, hanging in the darkness, blue and white, and impossibly beautiful, a fragile island of warmth and life in an ocean of silence and starlight. Where are you listening from tonight, and what time is it there? I always love seeing how far these quiet journeys travel across the world. If you found a moment of peace here, please leave a like and subscribe for more gentle explorations of the cosmos, told slowly, told calmly, and told with the kind of quiet wonder that the darkness of space deserves. Wishing you a peaceful night beneath the stars. May your mind find rest in the quiet of the universe.